Hello students, how are you all? I hope you all are very fine. So today let's begin with a fresh topic. The topic for today is we will try to discuss the points which is noticed when a conductor is placed under the influence of a uniform electric field. A conductor placed under the influence of a uniform electric field, right? Now students, as we are aware, substances broadly can be classified into 3-4 categories. There are conductors, there are insulators, there are semiconductors, there are dielectrics as well, right? Conductors, we all are aware, these are the substances which conducts electricity. They have a large number of free electrons which act as charge carriers. Insulators, on the other hand, they are poor conductors of electricity. In spite of applying potential difference, or in spite of applying electric field, they won't conduct electric current, right? So these substances which are insulators, they do not conduct electricity because of scarcity of charge carriers. Now comes dielectrics. Dielectrics, actually they are also insulators. They are special type of insulators which produces, or in which the induced charges are set up on its faces under the influence of strong electric field. So under the influence of strong electric field, these dielectrics starts conducting, right? So that's the basic difference between insulators and dielectrics. And semiconductors, as you are aware, semi means neither extreme. These are the substances like silicon, germanium, whose conductivity is less than that of conductors but more than that of insulators, right? So these are basically the 4 different categories of substances: conductors, insulators, dielectrics, semiconductors, right? In the present topic, we will discuss conductors under the influence of uniform electric field. What are the changes which we will notice, right? So, this is suppose a conductor. Let us consider this to be a conductor. Now, as I told you, a conductor has a large number of charge carriers, and charge carriers in a conductor are free electrons, the valence electrons, which are present in the outermost shell of an atom. So a conductor has large number of free electrons inside it. It is obviously made up of atoms and molecules. All the atoms in normal state are electrically neutral. So this conductor as a whole is also electrically neutral. There is no net charge, right? But there are a large number of free electrons inside it. These are the 2 plates, and in the space between these 2 plates, a uniform electric field exists, represented by E, or it may be represented by E naught. This is the applied electric field, right? So it is active from positive plate to negative plate. Set of parallel equidistant lines represent uniform electric field. Now what happens is, we will place this conductor in the space between the plates of the capacitor. So that's diagram C. Place the conductor in the space between the plates. So that's diagram C. Now what changes we will notice? That needs to be discussed, right? First and foremost, as I've told you, this is a conductor having large number of free electrons. So as soon as it comes under the influence of electric field, the charged particles, which are electrons, will experience an electric force. And electron being negatively charged, it will experience an electric force in a direction opposite to that of the applied field, right? So this is the force that an electron will experience. It is minus E naught vector. So this is the applied field. So electron inside the conductor will experience an electric force against the direction of the electric field. So the face of the conductor towards the positive plate will acquire net negative charge, while on the other hand, the face of the conductor, which is towards the negative plate, due to the deficiency of electrons, will acquire a net positive charge. So basically, redistribution of electrons will take place, right? This is the first point. So as soon as the conductor is placed under the influence of uniform electric field, then what will happen is, the electrons will experience an electric force in a direction opposite to that of the applied field. So all the electrons will come nearer on this face towards the positive plate. Now, the other face of the conductor, due to the deficiency of the electrons, will acquire positive charge, as it's pretty evident from this diagram. So, due to this redistribution of electrons inside the conductor, an electric field is set up, right? And this electric field is directed from positive to negative. That is, it is in a direction opposite to that of the applied field. Now, students, in the equilibrium condition, when static condition is achieved, then it is found that this electric field so developed due to the redistribution of electrons is oppositely directed, but in magnitude it is found to be exactly equal to that of the applied field. So as a result, they tend to cancel out the effect of each other. So thus, the net electric field inside the conductor is 0. This is a very, very important point. Again I repeat, due to this redistribution of electrons, an electric field is established inside the conductor, which is opposite to the direction of the applied field. But in the equilibrium static condition, the strength of this electric field developed inside the conductor is found to be exactly equal to that of the applied field. So they tend to nullify the effect of each other. They tend to cancel out the effect of each other. So as a result, the net electric field inside the conductor is 0. This is a very, very important point. The net electric field inside a conductor is 0, right? Also, there is no component of electric field along the surface of the conductor. What I mean to say is that, suppose we consider this part. Let us consider this part, right? This is positive charge. Let us consider electric field to be acting along this direction. Suppose making an angle theta with the surface of the conductor. I am considering this part, right? This part. So in this case, electric field can be resolved into two components. One of the component is this one, along the surface of the conductor. It will be E cos theta, while the other component will be perpendicular. That will be E sin theta. Now look, if this tangential component of electric field is present, E cos theta, then it would result into the movement of the charge residing on the surface of the body. So it will result into the surface current. But the charges reside on the surface of the conductor and they are in the static condition. They are not moving. So as a result, we conclude that this component must be absent. Now E is having non-zero value. Therefore, it implies that cos theta is equal to 0, or it further implies that theta is equal to 90 degree. So students, what I mean to say is that there can't be any component of the electric field along the surface of the conductor. It is because if this tangential component E cos theta is present, then it would result into the surface current, which obviously do not exist. So in order to maintain the static condition, this tangential component of electric field must be absent. And if E cos theta is 0, then we can safely conclude that theta is 90 degree. Theta 90 degree means the electric field lines, which earlier was represented by straight equidistant parallel lines, now after placing the conductor, the field lines will get modified. It will enter the surface of the conductor at right angle. It will emerge from the surface of the conductor also at right angle. So the diagram will get modified. It will be like this. It will enter the surface of the conductor at right angle, and also it will emerge from the surface of the conductor also at right angle, like this. So the field lines will get modified. So there won't be any component of the electric field which is tangential to the surface of the conductor. So the electric field would be perpendicular to the surface of the conductor, like this. Clear? So as the conductor is placed under the influence of uniform electric field, the field lines get modified. It enters or leaves the surface of the conductor at right angle. or in other words, there do not exist any initial component of the electric field. That is, in other words, there is no component of electric field along the surface of the conductor, so as to maintain this static condition. Right? Another very important point. In case this conductor is charged, then students, all the charge tends to reside only on the outer surface of the conductor. I repeat, if it is the case of a charged conductor, then all the charge on the conductor resides on the outer surface of the conductor. If you consider a Gaussian surface over here, this dotted line, it represents a Gaussian surface. Now if you apply Gauss theorem over here, we know that electric flux, which is closed surface integral of the electric field, it's equal to Q by epsilon, net charge inside. So electric field inside the conductor is 0, which implies that since E is equal to 0 inside the conductor, therefore Q inside, it would be equal to 0. So there is actually no charge inside the conductor. So in the case of a charged conductor under the influence of electric field, all the charge reside only on its surface. Right? All the charge on a conductor resides on its surface. Right? Another important point. Look, we have discussed electric field inside a conductor is always 0. That's the key point. So, electric field inside a conductor is 0. Since electric field in magnitude, we are aware that it's given by potential gradient. So, since electric field is 0, therefore dV by dr is equal to 0, which implies that V is constant. This is very important point. So students, the potential at any point inside the conductor, including its surface, is constant. I repeat, inside the conductor the electric field is 0. So the potential at any point inside the conductor, including its surface, is constant. Right? This is a very important point. Now look, over here, suppose this is point A, this is point B. At point A, point B, or at any point inside point C, at all the 3 points A, B, C, the potential must be same. So as a result, the work done in moving a charge between any 2 points on the surface of the conductor should be 0. Because those 2 points located on the surface of the conductor are at the same potential, isn't it? So this was again a very important concept, right? So before we proceed further, I must recapitulate all the important points. Students, please make a note of it and listen to me very carefully. Our topic is when a conductor is placed under the influence of uniform electric field. So this is the conductor I am talking about. It is a conductor, that substance which contains a lot of free charge carriers, which are free electrons basically. This region, the space between these two opposite charge plates will provide uniform electric field. Now this conductor is placed in the influence of this uniform electric field. So what we observe is, first point, the redistribution of electrons inside the conductor will take place. Obviously, the face of the conductor towards the positive plate will acquire a net negative charge, while the face of the conductor towards the negative plate, due to the deficiency of electrons, will acquire net positive charge. So due to this redistribution of electrons, an electric field inside the conductor is set up, whose direction is opposite to that of the applied field and magnitude exactly equal to that of the applied field, so as to attain the state of equilibrium, that is the static condition. So as a result, the internal field so developed due to the redistribution of electrons and the applied field being equal in magnitude and opposite directed, they tend to nullify or cancel out the effect of each other. So students, the net electric field inside a conductor is always 0. Please do remember it. The net electric field inside a conductor is always 0. Right? Still further, what we discussed is, Suppose this is point, this is any point on the surface of the conductor. Suppose the electric field is in the oblique direction and it makes an angle theta with the surface. So E can be resolved into two components. This is the tangential component along the surface and this is the normal component, right? Now if E cos theta were to be present, then it would make the charge on the surface to move in a particular direction, and that would in turn result into surface current, which obviously is not possible so as to maintain this static condition. Therefore, we conclude that there must not be any tangential component of the electric field. So the component of electric field along the surface of the conductor must be 0, from which we conclude that theta is 90 degree. That is, the electric field lines enters or leaves the surface of the conductor at right angle. It enters or leaves the surface of the conductor at right angle. Clear? Next was, if we apply, suppose there is a Gaussian surface, the dotted one. If you apply Gaussian theorem over here, the net electric flux which is given by the closed surface integral of the electric field, it's 1 by epsilon times the net charge. Now inside the net electric field is 0. Therefore, Q0 by epsilon would be also 0, which implies that net charge inside the conductor is 0. So in the case of a charged conductor, where the charge resides? If inside the conductor the net charge is 0, then where does the charge resides in case of a charged conductor? Students, in case of a charged conductor, the charge resides only on its outer surface. This is again a key point. In a charged conductor, the charge resides on its outer surface. Next one. Since the electric field inside the conductor is 0, therefore dV by dr is also 0, because E is given by, electric field is given by negative of the potential gradient. So in magnitude it's dV by dr. So if E is 0, then V is found to be constant. So it means that the potential at any point inside the conductor, including its surface, must be constant. It must be same. So if the potential between any two points on the surface of the conductor is same, then the work done in moving a charge between any two points on the surface of the conductor must be 0. So these are some very, very important and crucial points, right? Now what to do is, we'll consider a point P which is lying infinitesimally close to the surface of the conductor, lying outside. So what will be the strength of the electric field at this point? So we are going to find out the expression for the electric field, right? So next topic is, let's find out the electric field. Let us find out the electric field at a point outside a conductor and infinitesimally close to the surface of the conductor. So let's do it. Okay, suppose this is the conductor under consideration. This is the conductor. It can be of any shape. This is a conductor. And let us consider this is point P. This is suppose point P, where the strength of the electric field is to be calculated. Where the strength of the electric field is to be calculated, right? We will make use of Gauss theorem so as to solve this particular thing. So suppose this is point P, where the electric field is to be calculated, right? This is a charged one. This is a charged one. Suppose this is positively charged, this conductor. So our objective is to find out the electric field at point P, which is very close to the surface of the conductor. So what we'll do is, we consider a very small surface. This one. Let us consider this to be ds, the area of the shaded portion, and let it carries a charge of dq, right? So, in order to apply Gauss theorem, what we do is, we consider a cylindrical Gaussian surface. Such that one circular face of the cylinder is inside the conductor, while the other circular face of the cylinder lies outside the cylinder, right? So, the electric field at this point due to this positive small charge would be along this direction. This is the electric field. So let's try to find out the strength of the electric field. Students, here we can make use of Gauss theorem, right? So Gauss theorem states that the small electric flux, we are considering a very small area, the small electric flux associated, it would be given by E vector dot ds vector, and it is equal to dq by epsilon, isn't it? Now, what's the angle between the area vector and the electric field? It's 0 degree. This is ds vector. Again, it's given by the normal along the radius in the outward direction, right? So, what's the angle between these two? 0 degree. So, E ds cos 0. It is equal to dq by epsilon. It is the case of surface charge distribution. So, we'll make use of the term sigma. It is surface charge density. As students, it's given by charge per unit area. Therefore, dq may be written as sigma ds. Therefore, what do we get? E ds is equal to, in place of dq, you can write sigma ds. So, therefore, E is equal to sigma by epsilon. This is the magnitude of the electric field at point P, which is considered to be very, very close to the surface of the charged conductor. So, this is the expression for the electric field. Direction, it will be, if it is the case of positive charged conductor, it will be in the outward direction, right? So, students, this was again a very important concept. It can come in the short question category, 2 marks category. So, 2 topics we have done in this particular session. One is the points which we consider, or the points which we notice when a conductor is placed under the influence of electric field, right? So, I'll recap those points in a rapid way. The net electric field inside the conductor is 0. The charge resides on the outer surface of the conductor. The electric field lines enters or leaves the surface of the conductor always at right angle. The potential at any point inside the conductor, including its surface, is constant. And at any point just outside the surface of a charged conductor, the electric field is given by sigma by epsilon. Sigma is the surface charge density, right? Well, based on this concept, let me ask you a simple question. Suppose, let us consider a conductor, a spherical conductor, and field lines. So, you are supposed to state which of the diagram will represent the actual field line. Okay. This is suppose a spherical conductor. This is a spherical conductor. It is a spherical conductor. Right? And this is the center. And these are the field lines. Suppose this is the first field line represented by 1. Let us consider this to be the second one. Let us consider this to be the third one. And let us consider this to be the fourth one. First, second, third and fourth one. You are supposed to state which of the 4 field lines is valid, or which of the 4 will represent the actual field line. Okay. Let's consider the first one. Look, it is not entering the surface of the conductor at right angle. Right? This is not 90 degree. And also, inside the conductor, the electric field is 0. So, this is not the possible case. Right? Second one, although it is entering at right angle and leaving the surface of the conductor at right angle, but inside electric field must be 0. So, it also not represent the field line. It can't be possible. Third one, it is along the surface of the conductor. It is not entering or leaving the surface of the conductor at right angle. So third is not also possible. So the concept to be used is, when we consider a conductor, 2 points are to be noted in context with this particular numerical. First is the net electric field inside the conductor is 0. So all the three cases can't be possible. And second one is the electric field lines enters or leaves the conductor always at right angle. Now look, consider fourth one. Inside the electric field is 0 in case we consider fourth one. And also it enters, look, this is the radius. It enters or it leaves the surface of the conductor at right angle. So fourth one is the correct answer. So students, I hope I am able to clear your concepts. So these are the concepts which we will be making use of in finding the expression for capacitance of a capacitor when a conducting slab is introduced in the space between the plates of the capacitor. That we'll discuss in the next session. Till then, goodbye.